What are segment trees and why do we need them? Let's start with a very basic problem that I hope everybody knows how to solve. So imagine that we have an array that contains some integers. So for example, 5, 4, 1, 3, 2, 7. And I ask you to answer queries sum on a segment. This is a problem that occurs in many situations. So for example, I give you a segment, like let's call indices 0, 1, 2, 3, 4, 5. And I want to find a sum from index 2 to index 4 inclusive. Right? What would you do? I hope that most of you know that in this kind of situation we use prefix sums, right? And then we can calculate for every prefix of this array what is the sum, and then we can interpret this segment as a difference of two prefixes. So specifically, we put some numbers in between these indices, and for each of these vertical lines, we calculate the sum to the left. So here it's 0, then it's 5, because it's only 5 to the left of this line, then it's 5 and 4, so it's 9, then it's 10, 13, 15, and then 22, I guess, I'm not sure. Right, and then if we have a segment, we just look at its borders. This border is here, this border is here, and then we subtract these two numbers. 15 minus 9 should be 6. And this is indeed the sum of this segment, right? Because we have numbers 1, 3, and 2. Why does it work? Well, because this prefix corresponds to all these numbers. This prefix corresponds to all these numbers. So when we take this prefix, we take all the numbers that we need, but we also take something that we didn't need. So we need to subtract after that. So if we have a formula, sum on a, let's say, half-closed interval from left to right, this is how you would implement it, is just prefix R minus prefix L. Super simple. And this is like one of the simplest examples of a data structure. A data structure is when you have some kind of data, right, an array, and then we build a structure on top of it. In this case, we just calculate prefix sums. And then we can use this structure to answer queries, right? So data structure is some way to preprocess your data, preprocess your input, such that you can answer queries fast, right? Without this data structure, you would have to spend all of n time per query, but this way you can spend a constant time, right? Because you just take two prefixes and subtract them from each other. So in this case, we have preprocessing time all of n, and query constant of 1. But there is some specific property of this problem that we're using. So prefix sums can be used only in a very specific set of circumstances. So could you tell me, like, what exactly we're using in this case that you couldn't do in a different setting? This is a very vague question, but I hope you understand what I'm trying to get from you. So one of the things is that we're computing sum on a segment, right? What if we would compute something different? So for example, if you would want to compute, for example, XOR on a, so here we compute sum. Sum is all right. We can do everything with sum. Let's do this check mark green. If it would be, yeah, indeed, what you're saying in the chat is correct. We're using the fact that sum is invertible. So for example, we could also do XOR. There's also no problem. But if we would want some thing like minimum on a segment or maximum on a segment or a GCD on a segment, sadly we could not do it with prefix sums. Why? Because on a prefix sum we added some elements that we didn't want to add, and then we need to remove them. And the good property about sums is that when you add something, you can remove it by subtracting it, right? So if you had, I don't know, A plus B, you can go back to A by subtracting B, right? If you added B but you didn't want to add B, you can just subtract it. But you have minimum of A and B. and then I want to go back to A, there's kind of no way of going there. Because if B was smaller, I lost information about A completely. So specifically, if you would consider the following array where we have 0 in the first position, and then regardless of what numbers we have here, we have 3, 2, 7, 5, we want minimum on this segment, but all our prefix minima will be 0, right? So there is no information about this segment stored in prefix minima. The same way with maximum, GCD, and many other operations that are not invertible, right? Invertible. Okay. Another property that we're using is that our array is static, so we're not making any changes to our array. If I would change any specific element in this array to some, like this is not 4 anymore, but now this is 6, then I need to recalculate a lot of prefix sums, right? All of these prefix sums starting from here will have to be recalculated because they use this element 4 inside their sum. But we don't care about this for now. For now, we just want to calculate in a static array where no changes happen, all of these operations, regardless of whether it's invertible or not. So our main goal for now is to be able to answer queries for minimum on a segment. And maybe you've heard of this problem. This problem is a very well-known problem that is called RMQ, which stands for range minimum query, right? And let's learn how to do that, right? So even though prefix sums don't work, there are some more basic ideas that you could use. Like, what is the simplest way to answer queries for minimum on a segment? We can just calculate the answer to each query every time. So I just go through this segment and I look at the elements one by one and I calculate the minimum of them. So this will be like preprocessing, no preprocessing, right? I don't need to preprocess anything. But for queries, well, this segment can be very large, up to n, so I will spell it O of n time per query. So this is just brute force. There is another extreme. So in this case, I'm not preprocessing anything, and then I can spend O of n time per query. This is of course not great, because if I have n queries, this will be n times n quadratic time. That's a lot. But there is another extreme, where I can preprocess everything, precompute everything. And this is something that we'll call lookup table. In this situation, I just look at all segments, all possible segments, and I just compute the answer for these segments. So I have just some array, I don't know, let's call it D, where for every left bound and every right bound, I store some, not some, right, in this case minimum of all the segments on this array on this segment, right? And in this case, my queries are obvious. For every query, I already have the answer, so there is nothing to compute. But on the other hand, preprocessing now takes a lot of time. How much time does preprocessing take? What do you think? If I need to pre-calculate sum of all possible segments in the array. O of n squared, yeah. I mean, in theory, you could do even worse. You could do n cubed, because there's an n squared segments, and for each segment, if you just sum up the numbers, that would be n cubed. But of course, like if I fix the left bound, I could just increase the right bound, and I can just maintain the minimum on this kind of segment. So you can do it in n squared time, but that's still horrible. We don't want to do that. And we want to get some kind of middle ground, right? So in terms of preprocessing, right, we want something in the middle between nothing and a lot. And in terms of queries, we also want some middle ground between a lot of time spent per query, so O of n, and almost no time, so constant time. And in general, I want to say that So these two algorithms, brute force and lookup table, and also prefix sums, they all have something in common. And I want to say that basically all kinds of data structures that do this kind of queries on segments, range queries, they have something in common. I want to say that all of them store the answer for some segments. And then they try to, so they pre-compute the answer for some special segments, right? Pre-compute for special segments. And then we use these special segments, use them to answer queries for all segments, or let's say for any segment, right? What do I mean? For example, if you have prefix sums, right? Let's draw some array again. 3, 2, 1, 7, 5, 2. I store sums for all prefixes, right? This is basically the definition of prefix sums, right? And these are some kind of segments, right? I store n different segments. And if my operation is invertible, that's enough, because every kind of segment can be interpreted as the difference between two prefixes, right? If I have brute force, I'm actually also constructing my query segment from pre-computed segments. This is kind of hard to see, but just the segments that we use are just single elements. So my initial array basically stores sums or minima or whatever on segments of size 1, right? And then if I have a query segment, I just combine this linear number of pre-computed segments. That sounds kind of dumb, I understand, but you can think about it in this way. And if you do lookup table, well, in this case, you explicitly store answers for some number of segments, but actually this number of segments is all segments. So for all segments, we store the answer. And I want to say that all of these data structures that you maybe have heard of, maybe not, like segment trees, binary index tree, square root decomposition, disjoint sparse table, all of these data structures basically follow the same idea. They just choose the segments in a different way. And segment tree is just, we calculate some segments, and these segments represent a structure of a tree. That's everything segment tree is. So our goal, if you understand correctly, our goal is to calculate some segments, a rather small number of segments at the preprocessing stage, such that later on, whichever segment I'm given as a query, I can construct this segment out of some rather small number of segments that I'm initially given, right? Again, if your problem is invertible, then it's super easy. You just take two prefixes and you subtract them from each other. But in our case, we cannot do that. So we cannot take anything outside of the segment. We actually need to split it into segments. We don't have this negation, right? Okay, great. So this is our goal. And so what we are going to do in reality, okay, let's play some little game. So of course you have some kind of trade-off between how many segments you pre-compute and how many segments you need to use per query, right? So this query segment, it's created out of these special segments, pre-computed special segments. And we want the number of these segments to be as small as possible, right? So if I want to use only a single special segment per query, right? Only a single special, so with prefix sums, I use two segments, right? Two prefixes. And I'm still cheating, right? Because I'm subtracting. But let's forget about that. But if I only want to use one segment, I'm not allowed to use more than one segment, and I still want to answer every query, right? So if one segment per query, then how many segments do I need to pre-compute? So if I want every possible segment that exists in the array to be represented with one segment that I pre-computed. This sounds kind of dumb. How many I need? Yes, the answer in the chat is correct, n squared. You cannot do anything rather than do our lookup table, right? Because for every segment that you needed, you need to have this segment. Otherwise, you can't get this segment with only one segment, right? On the other end of the spectrum, we have, if we pre-compute only n segments, okay, no, forget about that. So what we're gonna do with segment trees is that we're gonna have not a constant number, but a rather small number of segments per query. It's gonna be of log n segments per query. But we'll drastically reduce the precomputation. So we'll only have a linear number of segments to pre-compute. Only a linear number of segments, but still every possible segment can be represented with a logarithmic number of the pre-computed ones. This is kind of magical. I don't know. If you think about it and you don't know this data structure, this sounds impossible. And I don't know. When I heard about it for the first time, my initial thought was to disprove it, because how on earth this could be true? But indeed, we're going to be able to do that. And I would say that this is a kind of interesting kind of game. If you want, after the lecture, I would recommend solving this exercise. So how far we can go, right? So as you understand, like, logarithmic number of segments is enough. If you allow to have logarithmic number of segments per query, then you have a very small precomputation, right? Of course, you can't have less than n, because at least you need to store all the initial values, right? So less than n is definitely not possible. So this is like two extremes, right? A lot of precompute or very little precompute. And what about in the middle? So obviously, if I have only one segment per query, I cannot do anything better than n squared. But what if I allow two segments per query? You could think that, well, what is the difference? One segment, two segment should be still n squared probably, right? But actually no, it drops dramatically. And I want to ask you, what is the smallest number of segments you can pre-compute to be able to answer any kind of query in just 2 segments? And this is basically data structure called disjoint sparse table. So as I said, all these data structures just solve the same problem, just in different ways. You can think about it if you want. Also an interesting question, what if I allow 3 segments? What's going to happen then? And so on. This is a kind of very nice game you can play if you want. But this is completely irrelevant for us. Let's come back to the topic of our discussion. Segment trees, right? So we want to pre-compute not that much, but be able to decompose any kind of segment into a logarithmic number of subsegments. Okay. So the idea that we're going to have is super simple. We're just going to do divide and conquer as a merge sort. So let's say that this is our initial array of length n. It has some values in it. I don't know. I'm not very good at 3, 2, 1, 4, 7, 5, 1, 3. Okay. And we're going to do something like merge sort. But in merge sort, we first split and then we merge back, right? That's why it's called merge sort. But let's just forget about the merge part. Let's only split. So what does merge sort do? Merge sort takes this array, splits it into 2 halves, and recurses on the 2 halves. right? So we're going to have 3, 2, 1, 4. And here we're going to have 7, 5, 1, 3. Okay. Then in each of these arrays, we're also going to split and recurse. Split and recurse. What are we going to have? Let's first draw all these segments. So here we're going to have 3, 2, 1, 4, 7, 5, 1, 3. And finally, we're going to get to single elements, right? 2, 2, 2. Great. You already see where the word tree comes from, right? Because this recursion of merge sort looks very much like a tree. 3, 2, 1, 4, 7, 5, 1, 3. After that, what would merge sort do is it would take and then merge back everything together to get the sorted array at the end. But we're not going to do anything like that. We're only interested in this decomposition. And I want to say that the segments that I drew are exactly the segments that we're going to store. So we're going to store the initial array, so the whole segment from 0 to n. Then we're going to store two halves, the left half and the right half, and then so on. So exactly the segments in our recursion tree of merge sort, these are exactly the segments that we're going to store. Right? There's a different way of looking at it. Let's look at it from, so here we looked kind of from top bottom, right? We look at the initial array and then we split it into two halves. Let's look at it from the other end, right? Let's look at the initial array. So the initial array is going to be 3, 2, okay, I'm not going to have enough space. Let's move a little bit down. 3, 2, 1, 4, 7, 5, 1, 3. These are the elements of our initial array. I want to say that, of course, we need to store at least all of them, right? All of these segments of length 1 we definitely need. Why? Because otherwise, how would you represent a query of length 1? Right? You can't represent it if you don't have this specific element. So we definitely need all of these elements. But also, I'm going to pair them up like an even index and an odd index together. And I'm also going to store the segment that is like a combined segment of these two elements, right? So let's give these indices, right? So this index is, in green, I'm going to draw indices, right? So this is index 0, 1, 2, 3, 4, 5, 6, 7. So these are indices of our initial array, and black are values of the initial array, right? So I just have segments of length 1, so just one value. Then I'm going to have segments of length 2, right? So 0, 1, 2, 3, 4, 5, 6, 7. And then I'm going to do the same operation over and over again. I'm again going to take, I'm going to take two segments and I'm going to combine them together, and I'm going to combine them here. I'm going to get two segments here. They would represent this. So every vertex here represents the whole segment on the bottom layer in its subtree. So this vertex, right, it corresponds to the whole set of these leaves at the last level in its subtree. So it's a segment from 0 to 3. Segment from 4 to 7. And then finally I'm going to have the root. I don't have space. Let's try to squeeze it here. I'm going to have the root here, and it's going to represent the whole array. So the segment from the segment from 0 to 7. Great. So here I draw what kind of segments I have. And for all of these segments and all of these segments, I will store sum on a segment or minimum on a segment or whatever you want, depending on what you want to calculate. And you can see that these pictures are very similar. This is basically the same picture. I just drew it in a different way, right? Okay. And this is the basic idea of segment trees. Now we just need to understand how to use them, why they're nice, how to implement them, and so on. But this is the basic idea. This is like what we're gonna store in some way, right? We have an array. We split it into some kind of, not split it, but we consider some collection of segments in this array. And then we use these segments to calculate values on any kind of segment, because now we can break any kind of segment into a small number of segments. Why we can break any number of any segment into a small number, it's unclear for now, but we're going to learn this later. You can notice that this tree has a very nice structure, but it's not a coincidence. It has a nice structure specifically because I chose the size of our array to be a power of 2. In this case, it's 8. If you have a power of 2, then if you split in half, you can always split in half, right? I have like, I don't know, 32 elements, I split in half, I get 16, I split in half, I get 8, I split in half, I get 4, 2, 1. If it's not a power of 2, there are going to be some troubles. For now, let's just ignore them. Let's just assume that our array has a length of a power of 2. If it doesn't, that's not a big deal. Let's say that we just extend our array to have the number of elements a power of 2. Like, let's say that a length of our array is n, and let's say that the closest power of 2 to n is 2 to the k. 2 to the k is at least n. Let's just add dummy elements at the end of our array, like let's add zeros at the end, so that the length of our array is actually 2 to the k. I want to say that it is not going to change our time complexity in any way, because any number n, it lives between 2 powers of 2. Like the closest and the previous one. 2 to the k minus 1 and 2 to the k, right? So if you go from here to here, you increase the size of your array by a factor of 2. And because n is in between, 2 to the k is at most twice large as n. So I will increase the size of my array by at most a factor of 2. Actually, strictly smaller than 2, but doesn't matter. If I increase the size of my array by a factor of 2, it's not going to change my time complexity. So, as I said way before here, I promised that we're going to pre-compute a linear number of segments, and every segment that exists can be represented as a logarithmic number of pre-computed segments. So let me keep my promise. First, let me explain why we have a linear number of segments in total. This is very simple. This actually will hold for any kind of tree of this form, not necessarily that works so beautifully. If you have any kind of tree like this, where every inner vertex has 2 children, it's always going to have the same number of vertices. So I want you to think about it in the following way. Let's look at the last level of our tree, and these are just individual elements of our array, right? Here we have exactly n elements, right? Because this is the length of our array. And then just think about these as kind of sets. So this is just sets of size 1. They contain individual elements. And then what does every internal vertex of this tree do? It takes 2 sets that are given in its children and it unites them into a single set. So it takes 2 sets and combines them together, right? So this takes elements like on positions 2 and 3, elements 1 and 4, combines them together. Here we also combine them together, and so on, right? And this is, you can think about it, some kind of process where initially we have n elements, and then in every operation we combine 2 elements together, and at the end, in the root, we'll have one single set that contains n elements. So just think about this process. We have n elements. After some process, you have only one set. Let's say n sets. We have n sets. And every operation, it takes two sets and it makes one set out of these two sets. So every internal node decreases the number of sets by 1. So if I initially had n sets and at the end I have one set, this means how many operations did I have to do to get from n to 1? No. So again, let's think about it. I have n sets, and in every operation, I decrease the number of sets by 1, right? I have two sets and I combine them together. How many operations do I need to make to decrease it from n to 1? In every operation, I decrease it by 1. How many times I need to subtract 1 from the number n to get back to 1? It's n minus 1 minus 1 minus, yes, indeed, n minus 1. Of course. Right? So I have n minus 1 internal vertices in this tree. So everything that is not a leaf, I have n minus 1, regardless of how what is the structure of this tree. In our case, the structure of the tree is very nice, but this works regardless. If every internal vertex has two children, the tree is always going to have n minus 1 internal nodes where n is the number of leaves. So in total, how many vertices you have? You have n leaves and n minus 1 internal vertices. So in total, you have two n minus 1 vertices. So a linear number, as I promised. You could think about it also in a different way. And somebody in the chat already said it. So in the last level, we have n elements. Let me draw it in a different picture. Like here we have n segments, one segment per element, and then we combine two together, right? So here we have twice less segments, so we have n half segments. Here we have n quarter segments, here we have n over 8. So we have this geometric progression of n plus n half plus n over 4 and so on plus 1. And I want to say that this is equal to 2n minus 1. Why is it the case? Let's just consider a segment of length 2n. And I want to say that every one of these summons is a half of everything that's left. Maybe you've heard of this story of a tortoise and I'm not sure what is the other animal, hare probably. And the hare always goes one half of the way, then it goes another half of the way, another half of the way, and so on. So here, half of 2n is n, so now we're left with n, then n half is half of the rest, n quarters is half of the rest, and so on, and at the end we have 1, which is half of the rest. So the only thing that we didn't take is 1. So we took everything from this segment of length 2n, except for a single element 1. So indeed, the sum is equal to 2n minus 1. But in general, just think about it as a geometric progression, which exponentially decreases, so the sum is proportional to the first term. Right? Okay. So we have a linear number of vertices. Here, you believe me? My other promise is that any kind of segment can be represented in a logarithmic number of subsegments. And this is actually non-trivial. Let's understand why this holds. Let me draw a new tree, because this tree is kind of... Maybe I can use it. Yeah, maybe I can use it. Let's just erase all of these circles that I drew here. And we can play some kind of game. I give you a segment, and you think, what is the smallest number of pre-computed segments that we can use to represent this segment? There's a question in the chat. Are we going to talk about lazy propagation today? The answer is no. Here we're trying to do the basic things. And from my experience, if you hear about segment trees for the first time, lazy propagation is just going to confuse you. So we're going to talk about that next time. Great. So let's start from a segment like this. So from index 1 to index 5. What is the I don't know, optimal way to represent the segment with the segments that we already have? Or maybe it's better to use this picture, I'm not sure. What do you think? Okay, let's use this picture indeed. This is the same picture, but just drawn differently. I want to represent this segments of values, so 2, 1, 4, 7, 5, using all these values that I pre-computed, and I want to use the smallest number of values. If you squeeze your eyes a little bit, you can understand that the optimal way is you could take this value, because you cannot take anything higher because it contains this 3. You should have this thing and you should take this thing, right? So you have 2 as a single element, you have 1, 4 as a single segment, and you have 7, 5. So you represented this segment of length 5 using 3 segments. So you kind of saved 2 operations. This is not very nice, but I want to say that in general, when n is large, it's going to be better. Okay, let's think about a new segment. Let's gonna make it longer, and it's gonna take this one also. Well, in this case, I want to say that not much changes, because this one we can only take it individually, because we cannot take anything higher. Like where this one is contained, here, and in all its parents. Like here this one, but we can't take any of the parents because the parents contain 3, right? And we don't want to have 3. So here we have to have 4 segments. But if something very nice will happen if I will increase the size of my segment even more. So if I'm going to take my segment from here up to the end, surprisingly, now I can do a lot of things, right? Like you could, like the simplest way is just add 3, but well, why would I take 1 and 3 if I can just take their parent? Instead of 1 and 3, you can take everything together. But now I again have the same thing. I have 2 segments that are siblings. So instead, I can take their parent. And now I again have only 3 segments to represent a very long segment of length 7, right? So I have elements 2, 1, 4, 7, 5, 1, 3, but I only have 3 segments. This one represents 2, this one represents 1, 4, and this one represents 7, 5, 1, 3. And you can play like this on paper, but it's kind of unclear what you would do in code, right? We need to do this in code, so we need kind of very rigid way of finding these segments. And that's what I'm going to show you now. So how to break a query segment into pre-computed segments. Okay. There are different approaches. Today we're talking about starting from the basics, so just taking all the elements one by one, and then trying to see whether we can optimize. So let me draw some kind of example again. We have this tree. Right? So at the bottom, I have my initial array. My initial array is stored here. And then on top of that, I draw my tree. And I want to show you a very nice property. So let's look at this segment. And initially, I just take every single element individually. But whenever you take 2 siblings, you can see that it's not optimal. if I take two siblings, what is the point of taking them if I can just remove them and instead take their parent? Because their parent contains exactly the sum or the minimum or whatever you store of the two children. So what is the point of taking two siblings if instead I can take a parent? And let's always apply this rule. Whenever I want to take two siblings, instead I'm going to take their parent. This is a very simple rule, but I want to say that this is already enough. So I want to say that we still have this rule. Here we can take these two guys, and instead of that we can take their parent. But now we have the same situation. You see, these are two siblings, so instead I can take their parent. And indeed, this is a very simple kind of segment. It's just represented by a single vertex, right? If you look at this vertex, what are the leaves in its subtree? The leaves in its subtree are exactly these four elements. So this was kind of cheating. Of course, it's not going to work like that always, but this is a nice idea. So this is like a perfect world example, right? In the perfect world, I have a bunch of different values. I want to find some kind of segment, and in the perfect world, they all split into some number of siblings, and then I can just take their parents. Their parents also split into some kind of siblings, and I can take their parents, and so on. This is a perfect example, but of course it's not going to be perfect every time. But I want to say that there's very little you need to do if the situation is not perfect. So specifically, let's look at a different example that we had. I guess it was this kind of example, right? From here up to, I don't know, here. Yeah. So in this case, it's not true that all of my elements can be split into siblings, right? So these two are split into siblings, these two are split into siblings, but this one doesn't have a sibling. But if it doesn't have a sibling, I mean, there's nothing to do, right? I'll just have to take it on its own. But for all the other ones, I can just take their parents. And this is the way I'm going to create the vertices, define the vertices that I'm going to use. The same idea can work if I have this long segment, right? I again start from the initial values, but then instead I can take these two vertices. Instead of these two vertices, I again can take their parent. And this is just some kind of bottom-up idea. I start at the bottom, and whenever I have siblings, I just, instead of them, take their parents. How is it going to work in general? Well, I have some level of my segment tree, and I have some kind of elements. Ideally, right, in a good situation, I just have all of these are siblings. But sometimes this guy's sibling is outside of the array. Then what I do is I just take this element on its own, and I just remove it from my segment. I don't care about it anymore. I already took it. And now everybody has a sibling, so I can just move to my parents. And now I look at a segment of my parents. In this case, these guys are siblings, but this one has a sibling outside of my array, right? Outside of my query segment. So I have to take this guy, and I need to decrease the size of my segment. Now it's here. And now from here I can go up, and now I only have one element, and I take this one element. And if you look at these red things that I took, and you look at the leaves that they have in the last level, they exactly cover the whole segment that I had. So this one covers these two elements, this one covers these four elements, and this one covers one. So in every kind of level, on every level, I have a segment of things that I want to compute, and maybe I need to take one off of each side, maybe or maybe not, depending on the situation. So the worst case is this, right? The worst case is that the first element on my segment is a right sibling of somebody who I'm not interested in, and the rightmost element is the left sibling of somebody I'm not interested in. And in this case, I need to chop them off, both of them. I need to preserve them, take them as they are. And for everybody else, I could just go to the higher level, because the higher level exactly covers everything here. And this way, I'm just going up the tree. On each level, I take at most 2 segments. And because there are not that many levels in the tree, there are actually log n levels. On each level, I take at most two segments. So in total, I'm going to take at most 2 log n segments. Again, why the depth of the tree is log n? This is just the same idea as with merge sort, right? I start with the whole segment and then I split it in half. So the length of the segment decreases by a factor of 2 every time. So it was n, then it's n over 2, n over 4, n over 8, and so on. So the depth is logarithmic. Because the depth is logarithmic, and on every level I took at most 2 segments. In total I take all of log n segments. And this is the last thing that I promised you, right? I promised that we're gonna pre-compute a linear number of segments, and every query segment can be constructed using a logarithmic number of pre-computed ones. How would you implement this in code? I'm assuming it needs to be done in log n. Great, this is a good idea. This is a good question. That's exactly what we're gonna do now, right? So we kind of understood the idea of how this all works, but this is very theoretical, right? There's some kind of tree that exists somewhere. How exactly are you gonna implement that? And this is what we're gonna do now. If I remember correctly. Yes, that's exactly the next point. So you could do exactly what I told you, right? You could create a tree, right? For that, you can create some kind of structure in like your programming language that's gonna store, I don't know, the bounds of the segment that this vertex represents, links to the left and right child, and some kind of information about the segment. But that's very complicated. Actually, you don't need it to be that complicated. So I'm gonna store my tree in an array. It could sound weird, but I'm gonna do that. So I'm gonna just number all the vertices going top to bottom, left to right, and then I'm gonna notice some very nice property. So let's start from the root, and we're gonna number the root with the number 1. Then this is gonna be number 2, 3, next level it's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And like, I don't know, I want to store minima on segments, right? So I decompose my thing into segments. For each segment, I want to store minimum, right? And then in position, so I'm going to just have an array that's going to have elements 1, 2, 3, and so on, 15. And for every vertex, I'm going to store minimum on this segment, right? So in position 1, I'm going to store minimum on the whole tree. In position 8, I'm going to store the first position of my array and so on. But now I need to somehow traverse this tree. Given a vertex, I somehow want to know what is the index of its parent and what are the indices of its children. So now I want you to look at the picture and see some kind of property. Given a vertex index, how can I compute indices of its children? So for example, given 3, I want to compute 6 and 7. Given 1, I want to compute 2 and 3. Given 6, I want to compute 12 and 13. What is the property? Do you see it? How to compute given vertex V, what are the indices of its children? That is a interesting kind of puzzle to solve. And indeed, there are some answers in the chat. Indeed, there are 2 times V and 2 times V plus 1. So for example, for 5, it's 10 and 11. 2 times 5 is 10. 2 times 5 plus 1 is 11. For 6 is 12 and 13. For 3 is 6 and 7, and so on. And I can leave it again as an exercise. Prove this fact. This fact. Right? Prove it. And what about the other way around? So now we know, given a vertex, how to compute its children. But what about going the other way around? So if I want to go from a vertex to its parent, you can again look at the picture. So I want to go from 11 to 5, from 6 to 3, and so on. And I guess the simplest way is here. How do I, having 2v, how do I go to v? Or having 2v plus 1, how do I go to v? Given the index of a vertex, what is the index of its parent? Okay, maybe it's not that simple, but the answer is you just need to divide by 2, right? And take integer part of that. So here I mean like division as in C++, right? Because you can see it from this picture. I need to go from 2v to v. From v times 2 to v, right? I need to divide it. And here also, if I divide, I get like v plus a half, but if I round it, it's going to be v. So this is a very nice property. Given vertex v, its children are 2v and 2v plus 1. And given vertex v, its parent is v over 2. And this is kind of why, in this case, we use this one-based indexing. So you can notice that we start with a root with index 1. Normally, in competitive programming and computer science, we do zero-based indexing. In this case, it's kind of like an exception because of this rule, right? In this tree, you can always divide by 2 to get to your parent. If you're going to shift everything and you're going to use zero-based indexing, you're going to have to change these things. So, for example, your children are going to be 2v plus 1 and 2v plus 2. And your parent is going to be this weird formula, awkward v minus 1 half. You could do that. There's nothing wrong with that. But it just happens that in this specific case, formulas get out nicer if you use one-based indexing. But note that this indexing has nothing to do with your array. So your array still probably is zero-based indexing. Just your tree is one-based, right? And what is nice about this numbering, right? So let me draw it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. What is nice about this numbering is that whenever I'm saying I have a segment, it's actually a segment of vertices, right? So they have contiguous indices. So in this case, I have to take this guy and this guy because they don't have siblings inside this segment. And after that, I go to the previous level. And to go to the previous level, I have like the left bound of my segment, the right bound of the segment. I just divide them by 2. I just go to a segment L half, R half. And I end up in a segment on a previous level. So this kind of numbering helps us to have a very nice structure. So in this case, we have to take both of these vertices because they don't have siblings inside our segment. And our segment will be decomposed into these 4. Prerequisites, this time basically nothing, but merge sort tree, if you know it, that's great. Yeah. Okay. So how to build this tree? It's kind of simple. We just put our array in the last level, which is starting from index 8 in this case. And you can notice that we start with index 8 whenever the length of our array is 8. Regardless of the length of our array, like n is any power of 2, you can see that it's always true that we start with 2 to the k, right? So the first index in the last level of our tree is always 2 to the k. This is because, as I said, you always have n minus 1 internal vertices. So if you start with 1, you end with n minus 1, and this vertex is always going to have index n. And then you have n vertices on the last level, so the last one is going to have index 2n minus 1. So you just put your initial array. So you have your initial array R. It has length n from 0 to n minus 1. And you have your tree. You store your tree. So yeah, there is a question in the chat. Vertices 9 and 14 are not, they're not apart. So when a vertex is not, so if your sibling is not a part of your segment, you just take this vertex. So we want to decompose our array. We decomposed it into 4 segments. Segments that correspond to vertices with indices 5, 6, 9, and 14. Yeah, you can't move up with them. You need to get rid of them. So this is your array with indices from 0 to n minus 1. This is your tree. As I said, you also store your tree in an array. We just copy this array to the second half of your tree. So from index n to index 2n minus 1, we just copy our array. And then for everything else, your value, like you could, in theory, for every segment, we know for every vertex there is some kind of segment, we can compute minimum in this segment. But that's kind of complicated. You can use the recursive structure of your tree, right? If you have a vertex and it corresponds to some segment, you know that it has children, 2v and 2v plus 1, that correspond to the first half of the segment and the second half of the segment. And in our case, we compute minimum on all segments. So if you already computed minimum on the left half and it's 5, minimum on the right half is 3, you just need to take minimum of these two minima to get minimum on the whole array, on the whole segment, right? If you know in the left it's 5, here it's 3, then in total the minimum was 3. So actually you just need to go here through all the vertices in the reversed order, right? So we're going in the tree bottom from bottom up. And for every vertex, we'll look at it to its children, on its two children, and compute the value using the children, right? Let me show it in code, because it could be a bit confusing like this. So we have our array. It could have length, not a power of 2. For now, we want it to always be a power of 2. So let's find a power of 2 that is at least the length of our array. So n is always going to be a power of 2. And while this power of 2 is less than the size of the array, I'm just going to double it. If I double it, it's always going to stay a power of 2. So at the end of this while cycle, and yes, I'm going to use C++ because I'm more familiar with it. And I think that for this kind of things, I think Python could be too slow for problems that require segment trees, but it really depends on the problem. You can solve many problems with segment trees with Python. If you don't understand something that in what I'm doing, if you know Python better, ask questions, and I'm gonna explain what is going on. So while n is less than the size of our array, I double it. So at the end, n is a power of 2, and it's at least the size of our array. So I can just resize my array with n. So basically I added some dummy elements at the end of my array. It's a power of 2 now. And now let's create our tree. So our tree again is going to be an array, right? What are you saying? No, what you're saying in the chat is not true. No, n is a power of 2. N is not the power, so it's not k, it's 2 to the k, right? Be careful. So let's build our tree. I build our tree, I take this array, and I want to create a tree. So, I mean, okay, I'm doing it like this. Maybe this is inside main somewhere, right? In main, your main function, this exists. And our tree is, I don't know, maybe it's global, but maybe it's better to create a struct that has it. But for now, I don't care about that. I'm just explaining how to write code. So we have our build function that just takes an array and builds a tree from it. So n is the size of my array. And then how many elements do I need to use? Let me change these two tabs. So how many elements do I need? My last index is 2n minus 1. So I need 2n elements. So let's resize my tree with 2n. And then what did I say? I take my array and I copy it in the tree starting from index n. Let's do that. Copy, array begin, array end, at index n, tree begin plus n, right? Starting from index n, it's gonna copy my array here into these indices in the tree. Great. And now everything that is left, so I now have the values in the leaves, and now I need to go up in the tree, and for every vertex, I need to compute the value in this vertex as the minimum of the two children, right? Going bottom up in a tree, in my case, is the same as going indices in the reversed order, right? I'm just going this way, up the tree. So my first leaf has index n, so I'm going to start from index n minus 1. From n minus 1 up to 1, my tree v is computed from its children. Children have indices 2v and 2v plus 1. So it's minimum of tree 2v and tree 2v plus 1. And this is it. Just like 5 lines of code, and we computed our segment tree. Now, what do we need to do? Okay, let me first tell you how much memory we use, right? So here it could look like we're using 2n memory, but you should notice that here we also first increase the size of my array. So I first had an array of length, I don't know, m, then I find a power of 2, m, that is at least m. This could increase the size of my array by a factor of 2, right? For example, if m is like 2 to the k minus 1 plus 1, it's just 1 larger than a power of 2. In this case, I need to almost double the size of my array, right? And then I have an array of length n, but then I build a tree of size 2n. So in total, from my initial array to the tree, it could happen that I need x4 memory. So remember that segment trees could take quite some memory. There are ways to decrease it to 2n. We're going to talk about that later. For now, it's relevant, but that's not that big of a deal, right? That's not like a big problem to have 4n memory, 4m memory. Right, but remember that we not only wanted to build segment tree. Like if you just have a segment tree, it's kind of nice. In some problems, like people give segment trees as birthday presents. But it's not going to exceed memory limit. I mean, it depends on what n is up to, like 10 to the 7, then 4 times n memory is not that much. The stream, I think we're going to end in about an hour. I think it's going to be like 2 hours in total, maybe a little bit more. Right, so we built the segment tree, but we also want to compute minima on all possible kind of segments, right? And for that, we need this operation that I described before, right? So we take our initial segment and we want to half both of our borders, right? Where did I draw it? I forgot. Okay, here, right? We had this segment. We want to go to the previous level, right? We want to, instead of having L and R, we want to have L half and R half. But sometimes we have these border cases. If the left the left vertex of my segment doesn't have a sibling inside my segment, then I need to take it and move my left bound. And in this case also, if my right vertex of the segment doesn't have a sibling inside the segment, I need to take it and move my border. In what case do I move my border? So for the leftmost vertex in a segment, it happens when it's a right child. And for the right boundary of my segment, it happens when this is a left child. Right? So how do I understand that when I'm standing in some vertex with index L, how do I understand that it's a left child or a right child? What do you think? Given index of a vertex, how do I understand that it's a right child? In this case, right children are 3, 5, 7, 9, 11, 13, 15. Yes, it depends on parity. Because of this picture, as always, right? This is 2v, so this is even, and this is odd. So it's always true that my left child is always even and my right child is always odd. So if I want to go to the previous level, right, this is the picture I want, when all the elements in my segment are coupled as siblings. So in this case, this should be, vertex L should be the left child and vertex R should be the right child. So it means that vertex V should be vertex L should be even and vertex R should be odd. Right? So before going to the previous level, I want to make sure that my segment, the left bound of my segment is even, the right bound of my segment is odd. If it's not the case, then I just take this element and move my bound. And this is basically my whole the whole algorithm, right? But so we start, we have some kind of function, right? Find minimum on a segment from L to R. Again, we're gonna contradict some of the very known practices in competitive programming and coding in general. Here we're gonna think of this as a segment from L to R. Normally, a better practice in most scenarios is to think of a half-closed intervals. So it's from L to R, but R exclusive. In this specific case for us, because we're trying to make things as simple as possible, this is going to be simpler probably, because otherwise you're going to be confused. So first, we need to do a very important step, right? L and R are indices in the array. But I need to transfer from an array to tree, right? Because I start with, here I start with vertices on the segment from 9 to 14. But in my initial array, these had indices like 0, 1, 2, 3, 4, 5, 6, 7. So it was an array from 1 to 6, right? So I somehow need to transform my indices from array to tree. But this is easy. This is done exactly with what I drew here, right? Because we copied our array into the tree, but we shifted it by n, right? So index 0 becomes index n, index 1 becomes n plus 1, and so on. So any kind of index L in the tree is stored in vertex L plus m. So I just need to add m to all my indices to get vertices. So now L and R are not indexes in the array, but vertices in my tree. And now we start from the last level of recursion, of last level of my tree, and then I go up, 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 as I said. How do we do that? So let's store some kind of answer, which is gonna, like, we decompose our array into some kind of segments. And for each segment, we know the minimum, and then we need to take minimum out of all these segments. So we're going to store it in the variable answer. But initially, like, what if you want to compute minimum of the whole array? Imagine you have some kind of function that array minimum, right? You're given some kind of array and you want to compute minimum. You have initially your answer, and then you go through all the elements and you change answer's minimum of answer and array I, and then you return answer. This is how you would do minimum of an array, right? Just iterate over all elements and update your answer with this value. But here's the problem. What do you set initially? If it would be sum, you would set 0, right? You start with 0 and then you add values. But here we need to have some kind of element that is never going to be minimum. For that we normally use infinity, right? Infinity is just some kind of constant that is larger than all possible values in your array. Let's say 10 to the 9 in this case. If you don't know, this notation is writing 10 to the 9 in C++. So we start with this kind of neutral element, the element that doesn't matter, that's going to be replaced anyway. So we have to start with infinity. This code is irrelevant for us, it's just an example. And then we need to go up the tree. How long do we go up the tree? Well, while our segment actually exists. So while the left bound of our segment is to the left of the right bound of our segment, right? And what do? If the leftmost bound is a right child, so if it's odd, right? This picture, you should cement this picture into your brain. This is the most important picture in segment trees, right? You have vertex v and its children 2v and 2v plus 1. Yes, indeed, we could also use int max, and also there are in C, this is a C thing, and in C++ there are also some numeric limit things, but okay. Does it work now? Sorry. Is it back with the same microphone, or did the quality become worse? I don't know why it happened. Okay, let's hope that we're all good. Let's get back. Great. Okay, sorry about that. What were we saying? How long was I muted though? Let's hope that long. What were I saying? Okay, yeah. So we have a segment from L to R. And if the left bound is odd, I need to get rid of it. So I add this value to my answer, right? I take minimum of answer and this tree L. And then I need to shift my bounds inside my segment. So I need to increase L, right? So L plus plus, or L plus equal 1, whatever. And I need to do the same thing with the right bound. If the right bound this time is a left child, then I need to move it in, right? Again, looking at this picture, before moving to the next level, we need to have a nice structure of our segment. Our segment should contain paired numbers, right? So we should start with an even number and end with an odd number. If it's not true, so if the left bound is odd, we move it. If the right bound is even, we also move it. So if right bound is even, we again update the answer. We do exactly the same thing. And then we move our right bound into the segment. So we subtract 1 from this right bound. Again, you can do R minus minus. I'm just doing this so that I'm using the most basic C++ syntaxes so people from other languages can understand. And then don't remember to do the last step, right? This while loop is infinite. It's just gonna make L to be even or odd, and then it's not gonna change anything. After that, we need to move to the previous level. Remember, that's very important. To move to the previous level, we just take L and take its parent, which is L half, and take R and move to its parent, which is R half, right? So we just divide L by 2 and R by 2. And this is the whole algorithm that we have. At the end, we just have to return the answer. And this is it. This way, we actually implemented our range minimum queries. And answering the question in the chat, it's now very easy to understand the time complexity. The time complexity of building the segment tree is linear. You just copy some kind of array somewhere, and you do a linear sized loop. And the time complexity of a query is logarithmic. Why? Because you have a while loop in which you divide by 2 at every time. If you divide by 2 every time, it takes logarithmic time complexity, right? Great. So let me annotate this code. So if L is a right child, move it. If R is a left child, move it. Go to the previous level. And here, copy values to leaves. Compute all internal nodes. This is not that much code, right? Like, building is super simple, find minimum. I mean, there are some lines, but I think they all make sense, right? We just take our segment, we shift it by n so that now we have vertices instead of indices. That's kind of very important to distinguish, right? Between indices of your initial array and vertices in the tree, they're not the same things. And then we just move up, up, up. And before moving up, we just need to do some fix-ups. If the left vertex is a right child, we shift something. If the right vertex is a left child, we shift something. Yes, very correct. If you have n, the size of your array is n, and you have q queries, then your time complexity is n plus q log n, because n time for preprocessing and log n for every query. Great. But I want to say that a segment tree can do even more. So we did, what do? We just do static array, we do range minimum queries. But I want to do that a segment tree can also update your elements. So in our case, like, we had a specific array and it had some kind of values, 4, 7, 1, 2. And we pre-computed our segment tree and used it to answer queries. But I want to say that even if you can change elements, so I don't want this to be 7, now it's going to be 4 in our initial array, I still can do updates. And I still can do everything that the segment tree can do. Why is it the case? Well, why couldn't I do it, for example, with prefix sums? Let me remind you of that. In prefix sums, you store sums of every prefix. And then if I do an update, like I change this value, all these prefix sums are going to change. So in total, if I change, for example, the first element, then change the first element, then every prefix sum is going to change. And because there are n different prefix sums, it's going to take all of n time per query. But in my case, things are much better. If you look at our tree, right, we built on top of our array some kind of a tree structure. And I want to say that if I change a single leaf value, right, a leaf value is our initial array value, then not that much is going to change. So I update a single element, and a value in a vertex only depends on the leaves in its subtree, right? So the value on this vertex is minimum of these 4 elements. So if I change a specific value, it's only going to change its parent, the parent of its parent, and so on. So only its ancestors. So only vertices on the path from this leaf to the root. So only like the number of vertices that are going to change is proportional to the depth of the tree. And because the depth of the tree is log n, I only need to change a logarithmic number of vertices. So actually my segment tree has even nicer properties than what I told you before, right? I told you before that the nice property of our segment tree is that any segment can be decomposed into a logarithmic number of subsegments. But there is also another property, that every element is contained in only a logarithmic number of pre-computed segments. And because of these two properties, I can do both queries and updates. So what do? Right? We just change the value in the leaf, and then we go up. We already know how to do up. We just divide by 2. And then we recompute the value in all these vertices. Let's do that. So void update. I have some index I, and I have new value, right? The same way as with find minimum, we need to change from indices in the array to vertices of the tree. So we do I plus equal m, and set the value here to be equal to the new value. And now, while we are not in the root, so we're standing in this vertex, what do we need to do? We need to go to its parent and recompute the value. Then go to its parent, recompute the value. Go to its parent, recompute the value. And then when we're already in the root, we need to stop. I'm not sure I understand the question in the chat. Indeed, there are 2 children of every vertex here, but this part didn't change. So I don't need to change anything there. I only change the value here. Only values that are relevant to this vertex change. This value is only contained in the parents, right? So while I'm not in the root, I go to the parent. Going to the parent is always dividing by 2. And then I recompute the value here. Computation of values, we already know how to do that. We do it as in this build operation. Let's just copy it from here, right? Just it's not for v, but for I. So I compute it as minimum of 2 children. And this is it. This is my update function. I just set a new value in a leaf, and then I go up, recomputing all the values there. I want to give you some kind of advice about this line specifically. And I want to say, never try to be clever. It shouldn't be I at least 1. It shouldn't be. Because if it's going to be I equals 1, I'm going to divide it by 2. And I'm going to move to vertex 0. Vertex 0 doesn't exist. So that's not relevant. But you could do it, right? You could do it like that. It's not going to change anything because I'm just going to update tree 0 with minimum of tree 0. I don't care about tree 0, so you could do that. But the right way of doing it is I larger than 1. So while I'm not in the root, I go up. I cannot go up from the root. Yes, and if I want to somehow remove any kind of value, right? The absence of a value, as you can see from here, is having infinity stored there. So if I just set some specific index to be equal to infinity, the value there, then you can think about it as just removing some element from the tree. But be careful that I don't shift indices, right? I just remove the element from some specific position in my array. but the indices here stay the same. They're not shifted, right? That would be a different kind of data structure, like binary search trees. In my case, array is static. Not static, but like the indices of my array are fixed. You cannot just remove an index from an array, right? And I want to say that as soon as we have updates, this data structure becomes interesting already not only for minimum, but also for sum. Because a question of, okay, I'm gonna say about never be clever in a minute after I change my code to be for sum on a segment. Thank you. Because without segment trees, there's no simple way of solving this problem, like updating a single element and searching for the sum on a segment, right? Prefix sums cannot do that. So already, even with sums, segment tree can be helpful. Now I just want to talk to you about, well, here I wrote the code specifically for minimum on a segment. But what if I want to change it to be for a different iteration? I want to say that there is a very small number of lines that I need to change. So what if I want to calculate sum on a segment, right? What do I need to change? Let's see. Copying initial elements, well, there's nothing to change. Now let's look at this. Here I compute an internal vertex value as the minimum of two children. If I want to compute sum on a segment, instead of minimum of two children, I'm going to have sum of two children. So it's going to be 3 2v plus 3 2v plus 1. Right? Now, what about here? When I update, I need to do the same thing. So let's say to be updated. I don't know how to comment this. Let's just put a star. If I put a star, I mean that this is a line that has to be changed if we change what our tree wants to compute. Right? Here I also need to change it, right? My answer should be sum of all these values. I also need to change this line, right? Because if I calculate sum of elements, I need to start with 0, not with infinity. And this should be also changed, right? Instead of taking minimum of answer in tree R, I should take sum. Here I also need to change the same thing as here. I should compute sum instead of minimum. But for I instead of v. So all these lines have to be changed, and very little number of them. 1, 2, 3, 4, 5. I only changed 5 lines slightly, and now my my segment tree works for sum on a segment rather than minimum. And you can do it with many operations. One important thing to keep in mind, the same way as with prefix sums, if you store sums on segments, you could get overflow, right? Because you have n elements, each one of them is 10 to the 9. I have like 10 to the 5 elements. Okay, n is 10 to the 5. Each element is up to 10 to the 9. The sum of all segments is up to 10 to 14, right? 10 to the 9 elements, 10 to the 5 elements, each one is 10 to the 9. I get 10 to the 14. So I need to use longs. Remember that, right? Here I'm going to use longs here, longs here, and longs here. Okay. Increase the size of the initial array. Why do I need to change that line? I don't think there's any change. Like my initial array has nothing to do with the operation. It's just an array. I don't care. Yeah, I mean, there's no reason to change anything here. Okay, good. So when I said, why never be clever? Let's come back to that. So you could think that you're super clever, and if you're finding sum on a segment, you know how these values have to be changed. There's no need to recompute them, you would say, right? So imagine that initially this value was 4, and I changed it to be equal to 7. Okay, let me address the comment from the... Yes, when I do resize, I change the elements to be equal to 0, but I don't care at all what is stored in the end of my array, because I'm never gonna ask about questions that go outside of my segment. I'm never gonna use any information, any nodes that store information about these nodes that are fake. So I don't care at all actually what is stored there. Okay. So if I had an element that was equal to 4 in my initial array, and I changed it to be equal to 7, you could say that, oh, I'm super clever. I don't need to recompute all these values. I just know that this element was increased by 3. So I just added 3 to this element. So actually, in all these vertices, I'm going to add 3. And this is how the sum on these segments is going to change. I just add 3 on all vertices. So instead of doing this recomputation here, recomputing as, again, sum on the left and on the right, you're going to be, oh, no. I'm just going to compute the difference between the old value and the new value and the old value. And I'm just going to add it to all the vertices on the path to the root. Just my advice, never do that. Never do that. So indeed, in this specific situation, when we're computing sum on a segment, you can do that. That would work. But for example, if you want to compute minimum, there's no way to do that. Again, the reason is sum, you can undo operations, right? You can subtract back. With minimum, you cannot subtract. Right? If you minimize for something, you cannot go back. But also because this way is super error prone. If we're gonna try to be clever and like think, oh, how are values updated? I'm gonna just do this update. A lot of the time you're just gonna make a mistake. There's no need. Just always recompute all the internal vertices with one simple rule. You always recompute a vertex as you take the value in the left child, you take the value in the right child, you combine them together. You never try to do anything smarter than that. Okay. Great. I don't know. To me, this is super fascinating because just think about it. You have a million elements. Let's say you have a million elements and I want to find minimum on any kind of segment there. And I just computed a small number of things and I only need to look at 40 different values in my array, in my tree, right? Because a log of 10 to the 6 is 20, and I use at most 2 times log vertices. So I only need to look at 40 different values, and I know the minimum on the whole segment. The length of the segment can be like 10 to the 5, 5 times 10 to the 6, anything. And only by looking at 40 different values, I can know the minimum on the segment. This is, I don't know, mind-blowing, absolutely mind-blowing. This is, I don't know, definitely the best data structure, like the nicest data structure there is, I would say. Okay. And yeah, we changed our tree to now compute minimum, sum on a segment, not minimum, but you can change it in any way to do any kind of operations. We already did minimum, you can do maximum. Maximum is super similar to minimum. I guess the only things you need to change is you need to change all the minimum to maximum. And instead of having infinity as the initial value, you're gonna have minus infinity, right? Or you can have GCD, right? You can have product, anything like that. And the only thing you need to change is this operation. So what do you do with the values? In this case, we always add values. If it's going to be minimum, you always take minimum of the values. And the other thing you need to change is the initial value. Some kind of neutral element. You can do it without a neutral element, actually, right? For example, there's a trick, right? I can just set this to be equal to tree L, and then I initially just add 1 to L, right? I just take the first element out, and then I am left with the smaller element. You can do that, but people don't really do that. Normally, people just use a neutral element. When it's a sum, it's a 0. When it's minimum, it's infinity. Let's just play a little game. I'm gonna give you operation and you're gonna tell me neutral element. So if I'm trying to find a sum, what is the neutral element? What is the neutral element for sum? 0. Yeah, adding 0 doesn't change anything. For minimum, we already talked about that, it's infinity. Because if I take minimum of something and infinity, this something doesn't change. We still have this a. If it's maximum, it's going to be the other way around, right? It's going to be minus infinity. Taking maximum with minus infinity doesn't change anything. What about product? If I want to store product of elements in a segment, be careful, right? With product, like if I multiply a bunch of numbers, it's going to overflow integer very fast. So probably it's going to be product modular, but that's not important. Yes, neutral element for product is 1. Whoa, what's going on? What's going on? 1. If I multiply by 1, nothing happens. And the last example, the hardest one, not that hard, but what about GCD? But if I'm trying to find greatest common divisor on a segment, what would be the neutral element? So GCD of A and what is equal to A? The answer is 0. Yes, taking GCD with 0 doesn't change anything. Great. Okay, so we're almost done. We're shortly are going to move to solving specific problems that you can solve with segment trees. Just one last thing is I want to make a shocking announcement that you don't need to do this. Yeah, how about XOR? That's a very good question. Okay, that's actually, okay, yeah, okay, sure, XOR. What do you think about XOR? What is the neutral element for XOR? The same way as with sum, it's also going to be 0. Yeah, XORing with 0 does nothing. What is interesting about XOR is doing prefix sums with XOR. This is kind of a tangent, let me take you. So if you have prefix sums, to get a segment, you take right prefix sum, and then you subtract the left prefix sum. So this is like a negation. For sum is minus. But what about XOR? If I have prefix XOR on the big segment and prefix XOR on the left segment, what do I do with them? I actually need to take XOR of them. So XOR is this weird operation for which the negation of it is it itself, right? Because A XOR A is equal to 0. So if I want to undo this A, I again XOR with it. But that's a tangent, that's irrelevant. Let's go back to our problem. My wildest claim is that you can just remove all these lines. So I told you, the structure so that the structure of our tree is nice and everything, we should change should change the size of our array to be a power of 2, blah blah blah. But actually, we don't need to do that. And for now, let's just forget about the tree. Let's just think just in terms of our array. So what is our array? In our array, we just store some elements at the end of the array, and all other elements have this property that tree in vertex v, the value of the array in index v is just like minimum or sum minimum of its children. 2v and 2v plus 1. Right? You can think about it even if there's no tree. Just this is some kind of array that works like that. And then let's say that my array is stored again from indices n to 2n minus 1, where n now is not even a power of 2, it's any number. And I have a segment from L to R. Well, if this is even and this is odd, like the good case, then it is true that if I just look at a segment from L half to R half, it's still true that all these values store pairs of values here, so the sum on this segment is the same as the sum on this segment. So I don't care about whether there is tree or whether there isn't a tree. This property still holds, right? So actually I can use exactly the same code, exactly the same, nothing changes. But n doesn't need to be a power of 2. If we look at the actual tree, let's see what's going to happen in that case. So let's say that n is equal to 6. If n is equal to 6, our numbered vertices are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we're going to store our n is equal to 6. So we'll store our array starting from vertex 6. So we're going to start in 6 and end in 11. So actually our array is going to be stored like in a weird way. Its prefix is going to be at the end of the previous level, and its suffix is going to be at the beginning of our next level. But you see this very nice property that we start in vertex n and we end in vertex 2n minus 1. Who is the parent of 2n minus 1? You know, again, as always, this picture, where is it? Here, no, where is the picture? I lost the picture. Here, right? Children of a vertex are 2v and 2v plus 1. Parent of a vertex is v over half. So parent of 2n minus 1, this vertex, is, what is it? n minus 1. 2n minus 1 half is n minus 1. So you see that even though these guys use this level for parents, it's still disjoint from these guys, because these guys start from n, and these guys end at n minus 1. So there is no intersection. This is very weird, right? This stops being this nice tree that we had before, but everything still works. And this is a super cool property. So you can think about all your things that you're doing as if you have this perfect binary tree. But actually you don't need to change n to be a power of 2. So we're gonna forget about all this here. And this way, we're only gonna have 2n memory, right? Because our array has size 2n here in build. Not 4n as it was before. Okay, this is everything from the theoretical perspective. Now we're gonna solve some problems and understand how to use segment trees specifically in some specific situations. But from just how segment trees work, this is everything that I wanted to tell you. This implementation of segment trees is called bottom-up, because we start at the bottom of the tree and then we go up, up, up with our queries and with preprocessing also. But there is also a different one, top-bottom, top-down, right? Which is a recursive version. So we start in the roots, then we go down, and there's a trade-off. So each one is simpler in its own way. Don't tell me thank you for the lecture. We didn't finish yet, right? We're going to solve some problems, which is also a very important part of the lecture. So in our bottom-up approach, what are the advantages? It's super fast. Super fast. Maybe you've heard of something called binary index trees or fanfic trees, and the only reason people use them, okay, two reasons. One is it's super easy to code, and second, you're allowed to leave, of course, but don't. And the second property is that they are lightning fast. The queries are super, super fast. Like all of these data structures work in log n time per query, but constants may differ, right? So fanfic tree is super fast. And people use fanfic trees because they are faster than segment trees. But actually, if you do segment trees in a bottom-up manner, they are basically as fast as fanfic trees. So this thing is super fast. And this is a bit slower. Another thing is that it's easier to implement, understand, and implement. So why is it slower? Well, because it uses recursion. We do if you think about any kind of divide and conquer, like merge sort, probably you're using recursion. And here we're also using recursion, so it's gonna be slower. And the advantage here is that it's much easier to make it general. So any kind of problem you want to solve, it's much easier to think about it in this top-down way. So you could think about it as being like, what is the right word? More powerful. Almost everything you can do with a bottom-up segment tree, but it's probably gonna take more of your mental energy. So even though, like, from the standpoint of learning it, it could be harder, but when you already understand top-down segment trees, applying it for all possible things, like segment trees can do actually a lot more than just queries and segments. And we're going to talk about that in the intermediate lecture on segment trees. And with top-down, like, you just need to change a couple of lines here and there, and the whole idea is super rigid. With bottom-up, you need a lot of more ideas if you want to do the same things. So I would say that for beginners, and for most of the problems, you're good with bottom-up segment trees. I'm just telling you that at some point, you're probably gonna have to learn the top-down approach. Don't think about it as I have to do it now or soon. Like, there are many applications of bottom-up, and rarely in competitive programming you actually need this top-down. But just keep it in mind that this is a simpler, faster version, but there is a slower, clunkier, but more powerful thing. In terms of memory efficiency, you can't do this trick with not making a power of 2 with this top-down approach. But there are still ways to make it use only 2n memory rather than 4n. But yes, by default, this is 2n and top-down is 4n. Okay, great. It's time to stop mumbling. Let's solve problems. And the first problem we're going to solve, how many problems are we going to have? Like 4 problems. Let's solve 4 problems. The first problem we're going to have is find kth 1 on a segment. I mean, when I say problems, I mean applications of segment trees that are not as easy as the ones that I already talked. You already can use segment trees in your problems, where you can just reduce your problem to these segment queries, right? For example, I don't know, you have some kind of dp, and the value of dp depends on the sum of the values of dp on a prefix. I don't know, for example, dpi is equal to ai plus dpi minus 1 plus dpi minus 2 plus so on plus dp0. In this case, you can just store dp in a segment tree. To compute dpi, you just take sum on a segment from 0 to I minus 1, and then you update this value. This is actually a very simple formula. You can definitely calculate this dp using some formulas, but whatever, in general, right? And you can already apply it, but this is like a simple application, right? You're just reducing your problem to specifically find sum on a segment or find minimum on a segment. We're going to talk about some more interesting applications, right? So find kth 1 on a segment. What do I mean by that? You have an array. Your array consists of only 1s and 0s. And you're given a segment, L to R, and I ask you, find me the position of the third 0, third 1 on the segment. So in this case, this is the first one, this is the second one, and this is the third one. So I want this index, right? How do I do that? From L to R. First of all, I'm gonna simplify the problem a little bit. Okay, yes, actually there is a great answer in the chat that I should have said. Indeed, you can just do binary search, right? Because let's just create some kind of segment tree. I mean, okay, if you don't have updates, you can just do prefix sums. But if I have updates, so I can change values, then let's say segment tree. And I can just do binary search, right? So I have L, and if I have this index, like the third one, this is basically the third index where the sum on the segment is 3, right? So I mean, sum on a segment is equal to the number of ones on the segment, if I only have zeros and ones. And then I can do binary search, right? So the more to the right I go, the larger the sum is. So I'm trying to find the smallest segment such that the sum is at least 3 or equal to 3. So I can do binary search plus a query to a segment tree. This is going to be of log squared n time. And this is a thing that I would like you to remember. If you have binary search plus query to segment tree, a lot of the time you can just combine those together. Let me write it down for myself. So if you're trying to binary search your right boundary, a lot of the time, instead of that, you can use your segment tree. And this is something called descent. I don't know how the word descent is written. Descent down the segment tree. This doesn't look like the word descent should be written, but whatever. So why? You can just combine them to get just a single log factor instead of 2 log factors. Why? I just want to tell you that going down the segment tree is basically binary search. This is a super cool idea. Like, let's look at our tree. So imagine, let me give you the first example where I don't have a segment. I just want to find the kth one on the whole array, in the whole array. How would I do that if I'm already given, if my array is static, I have like prefix sums and I do binary search. I break my array into 2 halves. I look at the sum in the left half. If there are at least k zeros, then the kth zero is here. If there are less than k zeros, then I need to go to the right and search for the kth zero there, right? This is binary search. But I want to say that you can do the same thing with your segment tree. Imagine I have like 5 zeros here and 7 zeros here. I want to find, I'm only saying zeros. 5 ones on the left and 7 ones on the right. I want to find the third one. Well, I see that on the left I have 5, so I go to the left. Then I see that, for example, here there are 2, and here there are 3, right? In total there are 5, 2 here, 3 here. 2 is not enough, so I go to the right. And now here I need to find the first one, right? Because 2 are already here. So if I wanted to find the third in general, now I want to find the first one. And now I can just descend this binary tree, the segment tree, and find my needed one. This is exactly the same as what you would do with binary search, right? You're just halving and then finding which half you need to go into. And because your segment tree kind of already contains this idea of binary search inside it, there's no need to have binary search and segment trees separately. You can just do this descent down the segment tree. So how are we going to do it in our case when it's not the whole array that we're finding the kth one, but on a segment? I'm going to make a couple of simplifications. So first of all, you're given a segment and you want to find the kth one. I want to say that the right boundary has nothing to do with that, right? The kth one is only dependent on the left boundary. The only case is if there are less than k ones on the segment, then the kth one could be outside okay, if it's outside, that at the end I'm going to check that it's outside of the segment, and then I'm not going to take it into account. But in general, it only depends on the right boundary. So we can actually assume that our right boundary is just n. So we find on a suffix the kth one. And the second simplification I'm going to have is I'm going to assume that n is a power of 2, right? I just told you how to get rid of this condition, but in this case it's just going to be easier to always think that n is a power of 2. Why? Well, because of the following. So what our segment trees can do. Imagine our query to a segment tree. It basically represents our segment as some number of subsegments that we initially pre-computed. So I don't know, there are some vertices, like this vertex. I don't know how to draw it. There is some vertex here that represents this segment. There is some vertex here that represents this segment. Some vertex here that represents this segment. So you see, whenever we have like a right child here, we take this segment and move it. Whenever we have the left child here, we move it and go up. The nice thing now is that this condition is never going to happen, right? Because our right vertex, this is a perfect binary tree, so our right vertex is always a right child. So we're never going to do anything on the right. We're only going to do something on the left. So yes, we use segment trees as computing minimum on a segment. But you should remember that actually what segment tree does is it decomposes any kind of segment into a logarithmic number of pre-computed segments. So actually, I break down my segment from L to n-1 into a logarithmic number of subtrees. Logarithmic number of vertices, right? And now, I don't know, I want to find like the fifth one. And I store here how many ones there are. So basically the sum in the segment. So for example, there are 2 ones here. There's one here, and there are 7 ones here. So I just go up, up, up. There are 2 ones. That's not enough. So I get rid of them. But because there are already 2 here, now I need to find not the 5th one, but the 3rd one. Now I go up, up, up. I look at this segment. This segment is again not interesting because it only has a single one, but I need the 3rd one. So I need to decrease it by 2 and go up. And now I finally come here, and this segment contains 7 ones, and I want the 2nd. So indeed my answer is inside this subtree. And now I do exactly the same as what I told you when we wanted to find the kth one in the whole array, right? Now my question is, I just have a vertex of a tree, so I have a subtree, and I want to find the 2nd one in the subtree. And for that, I just descend down the tree. Again, like in binary search, either go into the left or to the right. So you see now the structure of our operation to the tree is a bit different, right? We first go up, 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 and then we go down. So before we always went up, now we go first up and then down. And this way, we can find the kth one on a segment. But actually, again, there is a trick that you can also reduce this problem to this one, right? And this trick is called prefix sums. So if I want to find the kth one on the suffix starting from L, I can just ask my segment tree how many ones there are to the left, and let's say there are like 5 ones. If I wanted to find the 3rd one on the segment, it's the same thing as the 8th one in the whole array, right? Because there are 5 here that I don't care about, and after that I want the 3rd one. So I could just find the 8th one in the whole tree. So I could make one query to the segment tree and then do one descent from the root. But this only works in the specific case, but this idea of descending down the segment tree, as in combining binary search and queries to a segment tree into a single log factor rather than 2 log factors, is a very general idea that can be used in many situations. Okay. The second problem that we're going to talk about is, I would say, kind of surprising. So what did we learn to do? We can find query on a segment, and we can update in a point. By in a point, I mean updating a single element of your array. But what if we reverse this idea? What if we query single elements but we want to update whole segments? So for example, I want to add 5 to all the elements in a segment. So this plus 5, this plus 5, and so on. I can do that. For that, I need a crazy idea of just switching these two functions, right? So right now, normally, what my segment tree does, it stores sums on segments, and then if I want to take some segment, I combine it from the things that I store there. Let's reverse this idea. In my segment tree, a vertex of my segment tree is going to represent, like if I have value x here, it means to all the values on the segment, you have to add x to all the elements there. And then my find will become my update. So I go up the tree. So to find a value of a specific element, I need to learn how much I want to add to this element. Which vertices correspond to my element? Only the parents. So I need to go through all the ancestors, look at what they want to add to us. So this one says add 5 to all the elements, this says add 6 to all the elements, and so on. And then I just need to sum up all these updates to get the value of this element. So I kind of switch places of the functions update and find, right? So what is going to happen? Let me copy this. So this is now going to be update segment from left to right, and I'm adding a value x, right? So what am I going to do? I'm going to start my descent, and for every tree L, I need to add x here. So I decompose my segment into a logarithmic number of segments, and for each one of them, I add x. So tree R plus equal x. And then I don't return anything because because it's an update function. And now I want to query value. I only have a single element I. And here I start with an answer being 0. And I go, what do? I go up. Say I start with value tree I. And I go up. And I add tree I to the value. So I sum up all the values on the path to the root. And now I have updates on segments and queries in points. So I just changed the roles of the function update and query. This is a super surprising idea. And now my exercise to you is, can we somehow combine these ideas to have updates on segments and queries on segments? Think about it after the lecture. We're going to talk about this next time. This is a very nice exercise. So if we can do some kind of updates on segments and we can do queries on segments, maybe we can do both somehow? Let's think about that. Okay, great. But there is an alternative way to solve this problem, actually. So this problem of adding something on a segment and querying in single element. And the idea here is using difference arrays. This is kind of cheating. So what is a difference array? This is like the opposite of a prefix sums. So difference array is, you have an initial array, and it's gonna store differences between consecutive elements, right? So it's like -2, -2, 1, -1, 4. And then if I'm adding something on a segment plus x, then all these differences here are not gonna change because I add x to both of these values. So the only things that are gonna change are like here on the border, right? So here, this element is added x, but this is not, so I have to add x here, and here the other way around. This value is not changed, but here I add x, so I need to subtract x. So when I do a segment operation in my initial array, it's only a constant number of updates in my difference array. But then if I want, okay, I'm gonna write 5 here as just the first element. But if I want to find a specific element of my array, this is the same as a prefix sum is my difference array. So like difference array is the opposite operation from doing prefix sums. So my initial array is the array of prefix sums of the difference array. So if I want to do updates, I can just change single elements. And if I want to query an element, I need to find sum on a prefix. So this way I can do it in a black box fashion. So even if I just given a segment tree, I can do this trick and solve the problem. Okay. Another problem is the following. Pre-last problem. We're almost there. I have an array, 5, 3, 1, 2, 7, 2, 5. And I'm given a segment, LR, and I'm also given a value x. And I want to find the number of elements on this segment that are at least x. So for example, if x is equal to 3, the let's say at most, yeah. The number of elements that are at least 3, in this case, these 3 are at most 3. If it's going to be at most 2, then it's going to be only these two elements. So given a segment, my query is find the number of elements that are at most x. There are no updates. You can do this with updates, but it's going to be harder. You need a different data structure inside your data structure. That's too complicated for us. Let's just do no updates. Here, we're gonna use something that is called merge sort trees. Even though it's some new word and it sounds very scary, but actually it's the same as segment trees. But the difference is, in segment trees, in every vertex of your segment tree, okay, you're fine, maybe. I want online. Okay, I see what you mean by offline, yes, but we want online. Merge sort trees, the difference with segment trees is just in segment trees, you store like a single element in every vertex. So for example, a vertex of a segment tree contains the sum of all the values in its subtree. But in merge sort tree, in every vertex, I'm going to store the whole segment that this vertex corresponds to, but not the initial values, but the sorted version. So I'm going to store the sorted version of the segment. Basically, this is just doing merge sort, but also storing all intermediate information, right? Let's go all the way back to where I was describing you the segment tree. Yes, you're just doing a tree out of the recursion of your merge sort. What do you do in merge sort? You take your array, you split it in half, and so on, but then you also want to combine them back. So here I have 3, 2, I merge them into an array like 2, 3. Here 1, 4, I merge these into 1, 2, 3, 4, and I'm gonna store all this information. So not all these initial segments like 3, 2, 1, 4, but the sorted version. And this is gonna work in the same time as merge sort, so it's gonna take n log n time, but also this time it's gonna take n log n space, right? Because in every vertex I store a lot of stuff. I have a logarithmic number of levels, and on each level I actually store the whole array. So I'm going to have n log n space also. And now I can just use my idea of segment tree again. Like, it's very important to remember that a segment tree is not just some black box that answers your sum on a segment queries. What does segment tree do is you give it a segment and it decomposes it into some number of subsegments. So it gives us a logarithmic number of vertices such that segments of these vertices cover the whole array. And now if I want to find the number of elements at most x in the whole array, I just find it for all of these vertices. But for all of these vertices, it's super easy, because each of these vertices stores a sorted version of my array. So for each of these vertices, I can just binary search and find how many elements there are at most x. For this vertex, I also binary search in its stored array how many there are at most x, and here. And this way, I spend log squared n time. So I decompose my array into a logarithmic number of vertices, and for each vertex, I run binary search. And in this way, in log squared n time, I can find the number of elements at most x. There is an idea called fractional cascading that can do it in log n time. Kind of the idea is, if you have a bunch of binary searches, you can replace it with a single binary search. But the constant there is so large that at the end, as people say, it feels like it works almost as slow as this log squared n solution. So this log squared n solution is actually good enough, kind of, most of the time. Great. We learned how to answer a lot of queries. Now let's just solve the last problem. And the last problem is going to be a real problem called LIS. Longest increasing subsequence. So what is the problem? You're given an array and you need to find some subsequence in this array. Just choose some elements such that they form an increasing sequence. And we want to find the longest such subsequence. 1, 5, 7, 8 is increasing. Let's say that it's 4. So this is a very known problem, and there is a very nice, easy solution that works in of n log n time using binary search and some clever ideas. But I don't remember clever ideas. I mean, I could remember it if I wanted, but let's solve this problem in a different way. Let's solve it by just looking at a simple dynamic programming solution and just speeding this dynamic programming solution using segment trees. So what is the simple dynamic programming solution? Let's say the DPI is LIS ending in AI. So our array is A. Let's DPI be the longest increasing subsequence, the length of the longest increasing subsequence that ends in this element. So this element is the last element of the sequence. How do I compute this? Well, I have this element AI. I just look at all possible previous elements in the sequence. And then I need to take the longest sequence here, and then I'm taking just one more element, right? I'm pretty sure that most of you have seen this problem. So DPI is maximum over all indices j that are before I, and aj should be also smaller than ai. dpj plus 1, because we're taking that sequence and adding one more element at the end, right? And we compute this left to right, and this will take all of n squared time. For every index, we need to iterate over all previous indices. It's going to take n squared time. I'm going to say that when you have such DPs, where you're computing some aggregated values over some segments or whatever, you can speed it up using segment trees, right? How are we gonna do that? If it would be only, like, if this condition wouldn't exist, it's just maximum for g smaller than I, we would just store this DP in a segment tree, and then we're gonna take, I don't know, maximum on a prefix and update a single value. But we can't do that, right? Because we have this another property. But I want to tell you that we can do the other way around. We can get rid of this property. It's kind of weird, right? Why are we recomputing using larger indices j? But actually what I want to tell you is if we're computing our DP from left to right, then when we're standing in index I, all the other DP values to the right are zeros. So I mean, if I take them, nothing's going to happen. Like, I'm not supposed to recompute myself using them. But if I do that, they're definitely not going to be optimal. So whatever. And now I only have maximum for all values that are smaller than AI. So what if I'm going to store my DP not in terms of positions, but for values? So like I have an array in position AI, I store DPI. And then I need to take maximum on a prefix. And then I can use segment trees. Here I want to do a couple of assumptions. First of all elements are distinct, because otherwise in position AI, maybe I want to store two different values of DP if I have two different values that are the same. And also all elements are kind of small. Let's say that this is just a permutation. So all elements are from 0 to n-1. Because it could be that AI is like 10 to the 9 and that I need a very large index. If I have these two assumptions, this is a super easy solution. I can just code it in like a couple of lines. So I'm just going to compute my DP in a normal order from 0 to n. And to find DPI, I just find maximum on a prefix from 0 to AI minus 1, right? On the prefix to the left of AI, and I add 1 to this value, right? I have an error in my notes. Let me fix it quickly. Okay. And then I just need to update my segment tree. So in position I set the value to be equal to DPI. That's the whole code. This way I compute the whole DP array. The whole idea is just storing my DP array not in terms of indices, 1, 2, 3, 4, 5, but in terms of values, right? So in index AI are stored DPI, and thus this update is just taking maximum on a prefix. Note that we still go through indices in the increasing order of indices, but we'll store these values in positions. Oh wait, what am I doing? Not right. I'm saying something and I'm writing something different. Yeah, so we update the position AI, not position I. Okay. If these conditions are not satisfied, so if I have equal elements or they are not from 0 to n-1, there is still a way to overcome it. The idea is that I don't care about the exact values of my array. I only care about which one is smaller, which one is larger. So I only care about the relative order of these values. And then you can use something that is called coordinate compression. And this thing allows you to replace the values in your array such that if one value was smaller, it's still smaller. If two values were the same, they're still the same, but the values are more small. And this is an exercise for you. How to get rid of these two assumptions. There's a comment in the chat. You're kind of right. Yeah, you're kind of right. Just it's again going to become a bit harder, right? You need to update only in specific cases, but in general, you're correct. And I guess it's actually, yeah, it's always going to be better. Like it's never going to be smaller than the value that is stored there. So you may actually always update. You're just not going to have, like you also need to store these values somewhere. That's true. Okay, so in general, this is it. We have some exercises. I guess one of the exercises was, what is the smallest number of segments you need to cover any kind of query segments with 2 segments or 3 segments? That's the first exercise you have. The second exercise is proving that each vertex always has children 2v and 2v plus 1. What else? There was an exercise of think about how to combine these two things to have updates on segments and queries on segments. Finally, I have an exercise for you how to get rid of these two assumptions in this LAS. This is it. Please check out the links in the description. There's a link to a contest on Codeforces that I prepared for you. Please try to solve problems. Like listening to this lecture for 2.5 hours is great, but it's like a very tiny part of your education. Like the most important thing in competitive programming is solving problems. And please, like I gave you the code here, but please don't copy this code. Forget about, like, don't look into the lecture notes or anything. Try to remember everything from your head and write the code by yourself. This will help you remember everything and learn everything so much better. Because like just from hearing what I'm saying, you could feel like, okay, I understand everything. But then when it gets to practice, you will see that there are missing parts. And if you actually think about them by yourself, you're going to improve your understanding significantly. So that's a very important idea. Solve a bunch of problems and solve them on your own. So write segment trees, code segment trees from zero on your own. There are also like a couple of links to some materials that I used when I was preparing for this lecture, but this time not that many. Like when I was doing FFT, there were a lot of materials that I was using. Here are just a couple of things. And this is everything that I have for you today.